purpose of this video is to explore the functions and features of various display technologies. The objectives are to discuss the general overview of LED, VFD, LCD, and OLED technologies, understand how each technology works, learn the advantages and disadvantages of each display type, and see demonstrations of products offered by New Haven Display. An LED display is made of surface mount light-emitting diodes on a PCB in an encasement covered by a lens. Light-emitting diodes are solid-state devices in which electrons emit photons when falling into lower energy levels at the diode P-N junction. The wavelength of the emitted light can be selected to achieve nearly any color in the visible spectrum and even non-visible spectrum such as IR. LED displays are used in many different applications, including automotive, industrial, audio-video, and consumer products. Each segment in an LED display can be custom shape and size and is driven independently from the other segments. The segments can be driven with static voltage or multiplexed using PWM to control the brightness. As LEDs are current-driven devices, the forward current for full brightness is typically 20 milliamps per die. As more segments are turned on, the more current the display will draw. A display with 48 segments on will draw 960 milliamps at 100% brightness. Note that not all segments are normally on at a time. The typical forward voltage of common LEDs is 2.1 volt for red and 3.3 volt for blue. Operating temperature for LED displays is negative 25 degrees C to plus 85 degrees C. The typical lifetime of LED displays is 100,000 hours to half brightness for each segment. At half brightness, the display may still be usable, but the dim performance may be easily noticed next to a new display. Advantages of LEDs are low cost, high brightness, easy to read in dark or ambient light, wide temperature range, wide viewing angle, custom segments, each segment can be a different color, and ease of use and low processor requirements. Some disadvantages of LEDs are they can have high power requirements directly proportional to the number of on segments, and the custom segments can limit the ability to have dynamic information on the display. In a vacuum fluorescent display, high AC voltage is applied to a tungsten filament in a vacuum between layers of thick glass. When heated, the filament emits electrons toward the grid. Each segment or pixel in the display is a positively charged anode doped with phosphor, which glows when excited by electrons. The grid is then either positively or negatively charged to either accelerate or repel the electrons, thereby turning on or off a segment. VFDs are used in applications including automotive, industrial, appliances, and audio-video. Vacuum fluorescent displays can be made as just the glass with pins, or as a full module. As just glass, the filament AC voltage and the grid and segment DC voltages must be applied. As a module, the filament AC voltages generated onboard, and the built-in controller receives parallel or serial instructions and displays the desired characters. A color filter is then applied to the front of the display to change the traffic light green color to nearly any desired color. The typical power supply for the filament is 120 milliamps at 2.4 volt AC. The typical power supply for the anode and grid is approximately 10 milliamps each at 20 volt peak to peak. Total power for a VF module is typically 300 milliamps. Operating temperature for VFDs is negative 40 degrees C to plus 85 degrees C. The typical lifetime of a vacuum fluorescent display decreases as the size increases, but is typically between 50,000 to 100,000 hours to half brightness. At half brightness, the display may still be usable, but the dim performance will be easily noticed next to a new display. Some advantages of VFDs are their wide viewing angle, high brightness and easy to read in dark or ambient light, wide temperature range, and the rugged high-performance technology with a long lifetime. The disadvantages of VFDs are the plain glass requires AC and DC voltages, the module requires high power to drive the filament at all times, high cost, and a filter is required to get your desired color. crystal displays are made by filling a liquid crystal material between two pieces of polarized glass. In the normal state, the liquid crystal molecules are aligned. Since the two glass layers are polarized in perpendicular directions, the light from the backlight or reflector is blocked. When a segment or pixel is blocked and dark, it is in the on state. When voltage is applied to the liquid crystal, it twists in direct relationship with the applied voltage up to 90 degrees. The more the liquid crystals twist, the more light from the backlight or reflector is polarized to match the polarization of the front glass, making the pixel lighter toward the off state. LCD displays are used in almost any type of product, from automotive, medical, handheld, industrial, and consumer applications. LCDs require either ambient light to be reflected or a backlight to transmit light. LCDs are most often made as modules with a controller. The built-in controller provides the required voltages to twist the liquid crystal material. The controller receives parallel or serial instructions to display the desired fonts or turn on the selected pixels. LCD displays can be made in custom segment format, dot matrix character up to 4 lines by 20 characters, or full graphic. Character LCDs can have nearly any language of built-in fonts. Graphic LCDs have every pixel addressable, so any feasible character, icon, or picture can be displayed. The typical LCD module requires 5 to 10 milliamps on a 3.0 to 5 volt logic supply. The backlight for a small LCD typically requires 20 milliamps at 3.3 volt DC. The operating temperature for LCDs is negative 20 degrees C to plus 70 degrees C. The lifetime of LCDs is 100,000 hours, and the lifetime of the usual white LED backlight is 50,000 hours to half brightness. Some advantages of LCDs are their low cost, long lifetime, simple and low power and processor requirements. Many options are available for pixel and backlight color. They're easy to customize size. Transmissive, reflective, or transflective modes allow for readability from dark to direct sunlight. Some disadvantages of the LCDs are their low viewing angle, low response time, resulting in slow scrolling and animated graphics. The contrast gets dark at high temperatures and lighter at low temperatures, and the response time slows significantly at low temperatures. TFT displays transmit light the same way as the previously described passive matrix LCDs. The difference is that each individual pixel is turned on or off by a small transistor located directly inside the pixel. This active matrix of transistors provides much faster response time performance of each pixel, which allows this display to show real-time information and video. Each pixel on a TFT is actually composed of 3 subpixels, filtered for red, green, and blue light. By adjusting the brightness of each red, green, and blue subpixel, each pixel on a TFT is capable of displaying up to 16.7 million colors. The typical TFT requires 10 milliamps with a 3.3 volt DC logic supply. An LED backlight for a small TFT requires 20 milliamps at approximately 9 volt DC, which can be lowered by dimming. The operating temperature for TFTs is negative 20 degrees C to plus 70 degrees C. The lifetime of TFTs is 100,000 hours, and the lifetime of the usual white LED backlight is 50,000 hours to half brightness. The advantages of a TFT display are the full color display, fast response time capable of true video, and low overall power. The disadvantages of TFTs are their high processor requirements. The available sizes are mostly determined by consumer products, so there's very little customization. And the contrast and response time is also adversely affected by high and low temperatures. OLED displays are made of organic light-emitting diodes. An organic light-emitting diode is a solid-state semiconductor made of organic plastic polymer layers. When current flows, electrons from the cathode move to the emissive layer. Electrons from the conductive layer move to the anode. Electrons at the layer junction fall into holes and emit light. These displays require a built-in controller to provide the timing and voltage levels for the OLED. OLED displays can come in many different formats, including dot matrix character up to 4 rows by 20 characters with built-in language fonts, full monochrome graphic type up to 320 by 240 pixels, and up to full color graphic type featuring red, green, and blue subpixels similar to a TFT. OLED displays typically require around 2 milliamps at 3.3 volt for logic supply, but also require around 20 milliamps at 18 to 30 volt DC for contrast. Operating temperature for OLEDs is negative 40 C to plus 85 C. Lifetime of an OLED depends on the color. Yellow and green are 100,000 hours to half brightness. White is only 35,000 hours to half brightness. At half brightness, the display may still be usable, but the dim performance will be easily noticed next to a new display. The advantages of OLED displays are monochrome or full color available in character or graphic, a fast response time capable of true video, low overall power consumption, built-in controllers provide ease of use, greater than 160-degree viewing angle, high contrast ratio and brightness, and the contrast and response time remain throughout the entire temperature range. Some disadvantages of OLEDs are they can require up to 30 volt for contrast power, and some colors have low lifetime. While LCDs are the most common display technology, LEDs and VFDs reign supreme in some markets and applications, but the all-around superior performance, ease of use, and visual appeal of the OLEDs is resulting in their greatly increasing market share. For product upgrades and new designs, you should explore which display technology meets all your requirements, and of course, what looks best in your application.